Welcome back to Math 30-2. We are in Chapter 7, looking at logarithmic functions. So this is the second part to our lesson on 7.2, looking at the characteristics of logarithmic functions. And where we start today is by reviewing some ideas from the previous lesson. So we have 3 warm-up questions here. Yep. And I'll have you pause the video at this point, work through these 3 questions, and then restart the video once you've completed these 3. Well, here are the words that go through my head as I think about doing a question like this. I have log base 3 of 27. What this logarithm is saying is if 27 were rewritten as a power with 3 as the base. So remember that when we have this expression, this subscripted 3 here, we say is the base for the logarithm. So if 27 were written as a power base 3, what would the exponent be? That's what the logarithm is telling me. So what I'll do is I will rewrite it. So I have log base 3, 27 is 3 cubed. What is the exponent? Well, there are so many 3's there. Let me just highlight. This 3 in the exponent is my answer. It's the value of this logarithm. Let's do something similar with number 2. If 64 were written as a power with what's our base? The base is a 4. With 4 as the base, what would the exponent be? Well, let's rewrite it. 64, 4 times 4 is 16, times 4 is 64. So 4 cubed. What is the exponent? The exponent is a 3, and that's what a logarithm tells me. Question number 3. We want to rewrite this in exponential form. So again, when we're going to rewrite this in exponential form, we like to start, I like to start at least, with the base. The base of the logarithm is the base in my power. A logarithm is an exponent, so my exponent is x, and this is equal to what the logarithm was operating on, and we think of that as being a power in disguise. That's equal to the 40. So there we have exponential form for this logarithmic equation. Well, today, to begin with, we're just going to look at some more complex expressions, really just continuing on where we left off yesterday or in the previous lesson, whenever you watched it. So again, log base 1/5. If I was to rewrite this 1/5, so let me come back and I'm just going to drag this down from up here because I want to reuse these words. Those are the words in my head. If 1/5, which comes from here, were rewritten as a power with a base of 1/5. And that's coming from here. What would the exponent be? Well, it is already 1/5 to the exponent 1, so this equals 1. Let me think through these same words, but I won't recopy them for the next one. So now we're saying if 1 over 25 were rewritten as a power base 5, what would the exponent be? Well, I have log base 1/5. 1 over 25 is 1 over 5 squared, or 1/5 squared. What's the exponent? It's a 2. So thinking through questions this way really pushes us to understand what a logarithm is doing. But as you'll remember from the previous lesson, that's not the only way we could do it. What we could do is introduce a variable. And I could say, well, let's let this equal x. And then rewrite this in exponential form. My base is a 1/5. A logarithm is an exponent, so my exponent is x. And this is equal to my power, which is 25. And that gives me an exponential equation where I can solve for the x. Well, as we look at these two sides, we can write both sides as powers with a base of 5. So this 1/5, remember I can write as 5 to the negative 1, all to that exponent x, and 25 is 5 squared. Here, a power raised to an exponent, I multiply those exponents, so I'll get a negative x in the exponent on the left, 2 in the exponent on the right, power equals power, base equals base, so the exponent, negative x equals 2, and when I divide out that negative 1, I will get that x is equal to negative 2. And there's my answer for question 6. Well, I can't do that as easily for number 7. I could imagine that this is an x and this is a y. But let me go back to that previous method where I had that statement in blue. So I'll just scroll so we can see it again. So I'm just going to start with this one and say, if 16 were rewritten as a power with a base of 4, the logarithm tells me the exponent. So that's going to be the log base 4 of 4 squared. That's what 16 is equal to. What if 32 was rewritten as a power with a base of 2? Well, log base 2, 32 is 2 to the 5th. Log base 4 of 4 squared is the exponent of 2. Log base 2 of 2 to the 5th is the exponent of 5. And I get 7 as my answer. Next page. Here there are a couple questions for you to try, so pause the video at this point and try questions 8 and 9. Restart once you've finished. Well, there you can see my answer for number 8. I got 4. Question number 9. All those fractions, a little intimidating, but we'll just take it a little piece at a time. So let's start with this first bracket here. If I was to rewrite that 1/8 as a power base 2, base 1/2 I should say, that would be a 1/2 cubed. And then as I look at the next one, log base 7, 1 over 49 is 49 to the negative 1. So I'm going to do an in-between step there. This first one I already know, since I have a base of a half and a base of a half, this is just going to equal 3. The second one I need another step to get, so we'll have the log base 7 of 7 squared to the negative 1, power raised to an exponent. We can multiply those exponents, so I'll have 3 times log base 7 of 7 to the negative 2. Base equals base, so the value of the logarithm is just the exponent. So we have 3 times a negative 2, which gives us negative 6. So that just continues on from where yesterday or the previous lesson took us with some more complex fractional bases here today. Now we're going to shift gears and look at some application questions. First of all, we'll look at pH. Now, in chemistry, you may have done some pH questions, but try to think this through kind of in the more logarithmic way, rather than maybe the strategies you've used in chemistry. So pH is used to measure the acidity or alkalinity, how much base a solution has, and the pH scale is logarithmic with a base of 10. A logarithmic scale, it's useful for comparing numbers that vary greatly in size. And so that's why we use this scale. pH is defined by this equation below. So this P of x is going to be the pH, or the power of hydrogen. And the concentration of hydrogen ions is the x value. So a couple things here. We have pH, or the power of hydrogen, that's this part. And then the concentration of hydrogen ions, X, that's this value here. And that concentration is in moles per liter. You would be given that in a question if you need it. So in your textbook, you will have a chart that looks like this, and that shows the relationship between a number of different substances in terms of their pH value. Over here on the right, it gives us a little bit more information. A neutral solution, such as distilled water, has a pH of 7. So we think of this as being kind of the center of our chart here. And so this would be neutral. And then as we go in one direction, here we can see the acidity increases. And if we go in the other direction on the scale, we have the alkalinity increasing. So we think of it as an increase in both directions, but it's an increase of different things. Let's continue reading on the right-hand side there. So an acidic solution, such as POP, has a pH that is less. So the smaller this pH number, power of hydrogen, the more acidic something is. And there we go. Something that has a greater than 7 value for the power of hydrogen, like they talk about milk of magnesia here, has a pH of 10. We'd say that it is more alkaline. An increase or decrease of 1 unit in the power of hydrogen actually illustrates a change in the hydrogen ion concentration by a factor of 10. So what that's saying, well, let's continue here. For example, a solution with a pH of 4. So if I have a pH of 4, that is 10 times the hydrogen ion concentration as a pH of 5. So to go from here to there, we have 10 times the hydrogen ion concentration. So sometimes that's shown with an H with a little plus in the exponent. Well, let's look at an example. Back to the previous page. Number 10, the hydrogen ion concentration, X, of some solution is 0.0001 moles per liter. We want to know the pH. Well, we have this equation handily enough. And what we're given is the hydrogen ion concentration. We know the X value. So we just want to know, and I'm going to use pH instead of the P of X. And this is going to equal the negative log of my X value, which is 0.0001. Now notice again, no base was given, which means this is a base 10, which is what was described as we looked at the table. As we went from a pH of 5 to a pH of 4, it was 10 times as much. That's where the power of 10 came in. Well, as we want to evaluate this, we could plug it into our calculators, but why do that when we have a brain? Let's see, if we think place value, this zero is in the tenths, hundredths, thousandths, 10 thousandths. So this is 1 over 10,000, which is the same as negative log base 10 of 1 over 10 to the 1, 2, 3, 4. Yep, 1 over 10 to the fourth, which again is the same as negative log, keep that equal sign going there, base 10 of 10 to the negative 4. Now, we have to be a little bit careful. Remember there's this negative sign out in front of the logarithm, so I need to keep that negative sign out here. And then here, since I have log base 10 of 10 to an exponent, that exponent is the value of the logarithm. So I have the negative of a negative, which gives me a positive 4. So that would be the pH value for whatever this solution is. Question number 11. We're going to use the pH table to calculate the hydrogen ion concentration of lemon juice. So we'll look over here to the next page and we'll scan here, and there we find lemon juice. It has a pH of 2. So let's come back here Wrong direction. And I know that I have pH is equal to 2. So that tells me I'll have 2 is equal to the negative of log base 10 of x. In order to solve this equation, the first thing we need to do is deal with this negative sign out here. So let's imagine that that's a negative 1 times the log base 10 of x, and we will divide that negative 1 on both sides. So on the left, we'll have a negative 2 equals log base 10 of x. Well, now in order to figure out what this x is, probably the easiest thing for us to do would be to rewrite this in exponential form. So my base is a 10. A logarithm is an exponent, so the exponent is a negative 2. And this equals the power, which was an x. So I'm getting a hydrogen ion concentration of, let me just put this in decimal form, 0.01. And again, that would be moles per liter. Let's move ahead to the last page of this lesson. In terms of hydrogen ion concentration, how many times more acidic is solution A with a pH of 1.6? Well, I'm better start organizing my information here. So I have pH, I'll do a little subscript A. This is equal to 1.6. Compared to solution B with a pH, so pH with a subscript B is 2.5. How many times more? Well, when we want to know how many times more something is, we kind of think backwards and we think, oh, then we're going to divide to determine how many times more it is. For example, you see these trees on the right. If I wanted to know how many times taller the big tree was compared to the smaller tree, I would take this smaller tree and I'd say, well, I'd divide how many of these small trees fit into the big tree. So we'd say, well, if we start at the bottom there, that's where we go, and then we get a point here. I'm going to take this, that's once, and then this would be twice, and this would be 3 times and a little bit. So we'd say that the big tree is 3 and let's say 3.2 times as tall as the little tree. And the way we do it is we divide the size of the little tree into the size of the big tree. So in this question, what we're going to do is we're going to divide these values. So what we want to find in this question is how many times more acidic is A than B. So the one we're comparing to, the than B, will always go in the denominator. So I want to find XA divided by XB. And again, these X's are the powers of concentration. So that's what I want to be able to find in this question. I should say powers the hydrogen ion concentration, confusing the terms there. So let's go back to the equation. I know this is equal to the negative log of XA, and this will be equal to the negative log of, my X doesn't go there, log of XB. And then for both of these, I want to rewrite it in exponential form. So there, my base, oh, but not yet. I have to get rid of that negative sign first. Let's not be hasty. So we get rid of those negatives, and I should have had an equal sign over here. Sorry about that. We get rid of those negatives by dividing both sides by -1. So here I'll have -1.6 is equal to the log of A with this log of X subscript A. When I rewrite that, I'll have 10 to the exponent -1.6 equals XA. Let me switch colors here for this one, just to help organize the information a little bit better. I need to divide -1 on both sides, so I'll have -2.5 is equal to the log of xp, and then in exponential form, 10 to the exponent -2.5 is equal to xp. Again, this is the ratio that I want to evaluate. So we'll say xa over xb is equal to 10 to the -1.6 over 10 to the -2.5. And then we remember when we're dividing powers with the same base, we can subtract their exponents. So this will equal 10 to the exponent -1.6 minus the -2.5. And subtracting a negative, remember, is the same as addition. So this is equal to 10 to the -1.6 plus 2.5, which will be 10 to the exponent 0.9. We want our answer to the nearest tenth, so we can plug that into our calculator, and we will end up with our answer being about 7.9 times more acidic. And there we go for number 12. Almost done. One more question, different variety, not a power of hydrogen question, but a similar application, where now we're looking at earthquakes. This is check your understanding, so take a minute to read through it and examine the table on the right and see what you come up with for an answer. Restart once you're ready. Well, let's think it through together. Here in this explanation, the magnitude of an earthquake M, so this is just a number we use to describe how powerful the earthquake is. So here we're given the Richter scale magnitude. And you can see here a magnitude of 9.5, pretty severe, 1960 in Chile, near total destruction, massive loss of life. That's pretty extreme. Whereas down here with the smaller numbers, not as extreme. But again, it's powers of 10 as we increase. So as I go from 4 to 5, that earthquake we would say is 10 times more intense in terms of how much energy was released. So if I go from 4 to 6, it's 10 times 10, 100 times as much energy released. So that's the idea that we're looking at here. And again, as we look at this question, we're looking at how many times more energy. And often that kind of comparison comes up with these application questions. So similar to our previous question, we're going to be looking at a ratio. And since we're looking at how many times more energy, and here we're told x is the amplitude, which is an indication of the amount of energy released, we want to compare these two x values. Now, just to simplify it for me, I'm going to say that Haida Gwaii, BC, I'm going to just call that 1. And the Vancouver Island, I'm going to call that 2, just so I don't have to use so many variables. And what I want to find is Haida Gwaii compared to Vancouver Island. So I want to compare x1 to x2. That's what we want to find in this question. Now, we need to find the magnitudes. So over here, we look at our chart and we can find up here, there's the offshore Haida Gwaii, British Columbia. That was 8.1. And then we come down, we see here 3.8. That's offshore Vancouver Island. in 2011. So those are the two Richter numbers or magnitudes that we're going to use for a comparison. So we'll scroll down a little bit again here. Can't see the equation up there, but you can see it on your page. So I know that that magnitude of 8.1 is equal to, notice there's no negative sign this time with our logarithm as you look at the equation that's above. Guess I'll scroll up. There you go. So here's the equation. The magnitude is just equal to the log of x. No negatives involved. So the log of x1. And I'm going to rewrite this in exponential form. A little bit easier than the last one because I don't have to deal with that negative. My base is a 10. My exponent is an 8.1, and that's equal to the x1, the energy released in that Haida Gwaii earthquake. Second, we know 3.8 is equal to the log of x2. So 10 to the exponent 3.8 is equal to x2. And now we want to find that ratio of x1 over x2 as we compare Haida Gwaii to the Vancouver Island earthquake. Well, for Haida Gwaii, we had 10 to the 8.1. And you'll notice that I'm not evaluating this to a number. I could, and then we could divide it. But because these are both powers base 10, I just like to simplify first. So here I have 10 to the 3.8. And again, the dividing powers with the same base, I subtract their exponents. So 8.1 minus the 3.8. And that gives me a 4.3 in the exponent. And when I plug that into my calculator, I get 19,953 if I round times as much energy was released. So that's a huge difference, almost 20,000 times as much energy, where when we just look at the Richter numbers, we say, oh, it's not even 5 more, it's 4 and a little bit more. But that tells us how the scale increases in magnitudes of 10. Every time we increase by 1, it's 10 times more energy that was released. And there we go. So you have a couple applications under your belt and some more questions practiced. So there we go. Put it into words. And we have the measures of success and some questions to practice. Take care.